All right, I'm not going to read you the additional features of an isomorphism because I trust that you can read for yourselves. But I do want to point out this notation. When we say that it's a cyclic group G equal to A in our inequality symbols here, A is our generator. So we've got, for some A, element of G, and here H is a cyclic group where B is its generator. All right, so if we've got cyclic groups with the same order, then there's going to be an isomorphism between them. So that's pretty interesting, although not so surprising. All right, so let's look at this example. Now we've got our set of values S, so A plus B root 3, A and B are both rational numbers. There's this function that maps from S to S, and here's the function itself. So we're told that S is a group under multiplication, so we don't need to do the properties of group, but to show an isomorphism, we do need to show that it's bijective, and we need to show that operations are preserved over our f of A times B equals f of A times f of B. So we can start with any one of those. I'm going to start with the functions because I like those. So let's do f of A plus B equals f of A plus f, sorry, not plus. Our operation is not addition. Our operation is multiplication. All right, so I'm going to start with the left-hand side. So f of A times B, that's going to be f of, so in this case, maybe I shouldn't have used A and B because we've got A and B already. So I'm going to use different letters. So let's go with x plus y root 3 times, let's do x1, y1, x2 plus y2 root 3. All right, so we need to evaluate this multiplication. That's going to give us x1, x2 plus 3, y1, y2 plus root 3 times the quantity x1, y2 plus x2, y1. All right, so now I need to do f of this. Doing f of this means I'm going to end up with my output of x1 plus x2, sorry, x1, x2 plus 3, y1, y2 minus root 3, x1, y2, x2, y1. All right, so now I need to do the right-hand side and hopefully get the same thing. On my right-hand side, I'll have f of A times f of B. So f of A, I'm going to put in my x1, y1 and get out this. So x1 minus root 3 y1 times x2 minus root 3 y2. And now I just need to do my distribution, and when I do that, I'm totally going to end up with the same thing. x1, x2, negative, 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 negative makes positive, of course. y1, y2 minus root 3, x1, y2 plus x2, y1. All right, so we have shown that this is true. So it maintains structure. Now I need to show that my function is bijective. So we can start with showing injective. And you may remember, or you may not, and you may need to look it up, but to show injective, I need to show that f of x1 plus y1 root 3 is the same as, so I need to show that if these two are the same, then x1 equals x2, y1 equals y2. But of course, this is going to equal x1 minus y1 root 3 equals x2 minus y2 root 3. For these to be the same, x1 has to equal x2, and y1 has to equal y2. Therefore, it is injective. Now to show surjective, we need to show that every element in the codomain is also in the range. But if we think about our function, then we've got a minus b root 3, and our function is the set of all values defined here, all of the a plus b root 3, where a and b are rational numbers. But we started with a plus b being rational numbers, so every value in our range is also going to be part of the codomain. So f is surjective as range equals codomain for all a minus b root 3 element of our set. All right, so we've shown everything we need to show to prove that this is an isomorphism.